Hello, everyone, and welcome to Jaynky to the Max, a podcast where we talk about fantastic creations and the even cooler creators who make them. Today on the show, we have Ben Cartwright.
Hello, thanks for having me on.
Glad you could be here.
So Ben Cartwright is a graduate with a master's degree in electronics engineering and computer science in the UK, and he will shortly be starting as an electronics design engineer at UCRI RAL Space in Oxford. His primary interests are in CubeSats, novel small sat applications, and high-power rocketry, as well as developing the electronic systems inside of it.
Sounds so great.
Doesn't it? It's fantastic.
Glad you could be here. So tell us about what you do. You have the 10,000-foot view, but give us some details.
Sure. So I've actually been at UKRI for about 2 years now. So my day job is as an instrument electronics engineer on space telescopes. So we build all of the scientific instrumentation on solar observatories and weather satellites and Earth observation and things like that. And I've got a spin-off kind of startup company that does CubeSat platform development. That's called Citadel Space Systems. And that's basically a company trying to build CubeSat buses to fly science payloads beyond low Earth orbit and support kind of nanosatellite missions in more exciting locations than low orbit.
Well, so, CubeSat buses, that's not a term I've heard before.
So this is, if you imagine like a small spacecraft and it's got some payload in it, if you take away kind of a dedicated payload that's doing something in that mission, then everything else that's left is kind of the bus. So it's your communications, your command and control computing systems, or your power stuff, the structure.
Okay. So busing, I was thinking like a really futuristic space bus with like all these little CubeSats. Okay. So that's one of the things. Are you doing some work on the Flame Trench?
Yeah. So the Flame Trench is kind of a group of amateur space enthusiasts. Most of us are either students or actual engineers in the space industry. And we do lots of different amateur space-related projects. So one of which is a remote-controlled observatory called GAZE, which is something I've been working on a lot recently. The other one is a picosatellite or pocket cube called TFT Cube. And that's basically a 5-centimeter cube satellite that we're hoping to have some students fly some payloads on in the early 2020s.
Wow, that is so cool. You sound like a busy man.
A little bit, yeah. My development bandwidth is like 200% oversubscribed at the moment.
Oh, wow. So tell us about, we had Applied Ion earlier on the Space Month, but tell us about, like the other systems aboard the spaceship. Like, so you might have your propulsion. What does the energy storage look like? What is the instrumentation like? How does it all fit together and work together?
Sure. So typically you have some level of deployable solar panels or fixed solar panels, and they're all connected up to a power supply that's designed to be as efficient as possible, because you don't get much power input on really small satellites. So you have some level of hyper efficient power transfer, and that's connected up to several batteries or other power conditioning. And then everything else on the spacecraft runs off that. So you've got your computing systems, which handle the command and control of the payload and all of the other systems on board. You'll have some level of radio communication. Your payload will have potentially its own computer, and that will command itself. And less common amongst smaller satellites, but you'll have some level of attitude control. So that's kind of where you're pointing, or orbital control, which is propulsion. And that's roughly it. You can simplify it quite a lot at the top level. But when you're trying to fit so much stuff into such a small spacecraft, it's quite a bit more complex.
Yeah, especially in like pocket cubes. I mean, if you have all those systems working together and in such a hard, small space, that is really intense. So, you say you're a systems engineer?
Yeah, so I'm an electronics engineer by trade, and I tend to focus more on the systems side of things in the stuff that isn't my day job. So at RAL Space, I do most electronics design with a little bit of systems, and then I kind of pivot to more systemsy stuff at Citadel and at Flame Trench.
Okay, so what is? I actually have not heard the company you're working for. So does that supply? Is that a supplier for like the EU Space Agency, or is that like a?
So we are a government lab, kind of spin-off. So it's part of a major organization called the Science and Technology Facilities Council, and we are basically the provider of science equipment, large-scale science facilities for the UK. We do lots of international kind of stuff as well. RAL Space is kind of the division inside of that deals with space hardware. So we are a provider of scientific space hardware for UK and Europe, and we do stuff for the US as well. So yeah, we basically build parts of science and instrumentation at various different levels.
Wow, that is really cool. Wow, yeah, I just love hearing more about how that stuff fits together.
Yeah, we have a really long list of missions we've worked on. If you can have a look at the website online.
What's some of your most recent ones that you can share?
So we have an instrument on the James Webb Space Telescope called MIRI. That was assembled at RAL Space. That's the mid-infrared imager, I think it's called. We do lots of solar observations. So I think it's called SOLO, the solar orbiter that just launched. We did the SPICE instrument on that. All of the GOES-R series satellites have an instrument called SUVI, which operates and looks at the sun. That's one of ours. In fact, if you look at lots of the different solar observatories that are in operation at the moment, safe money is that we've been involved in it in some way. So we did instruments for stereo. We did SDO, the Solar Dynamics Observatory. I'm working on 2 different solar observatory missions at the moment called Punch for NASA and Lagrange for ESA. So yeah, we've got quite a lot of heritage in kind of like solar astronomy.
Nice. So a lot of this solar astronomy that you're looking for, it sounds like you have a lot of things for observing the sun going on and other bodies. What specifically do these units look at when they're looking at the sun? Just kind of curious.
So the idea for the 2 missions I'm working on at the moment is part of kind of a push for more space situational awareness. Mm-hmm. And basically what that means is there's a threat of things like space weather affecting things on Earth. And we don't understand that very well. And we don't have much in the line of early warning for that. So especially in the case of Lagrange, the idea is to go and put a spacecraft out in a distant Lagrange point, which is kind of like a stable point in space between 2 bodies. Okay. And the idea is to observe that solar weather from the side, kind of between the Earth and the Sun, instead of looking at it head on. And that will form part of kind of an early warning system and will give us some better understanding of how space weather propagates between the Sun and the Earth. And kind of in the same respect, the NASA mission is very similar, but that's just around the Earth, and that's 4 small sats, which will be observing the Sun at all times, kind of monitoring space weather and looking at the kind of effects near the Sun.
Oh, that is awesome. So it's basically kind of like right now, with us being able to observe the Sun only from Earth, it's kind of like having one point on a XY graph, but now with having satellites 90 degrees or to the side some, any amount really kind of helps you to be able to see on another axis, to be able to have more of a 2D look instead of just a one-dimensional.
Yeah, for sure. Exactly, yeah. It's about building up our awareness and having a much better understanding of exactly what's happening.
Oh, that is amazing. So, how long does it take between like the point where you launch those to be able to actually start getting like useful data, or is expected to get useful data?
It depends a lot where the mission is. So some are in low Earth orbit and they'll be operating within like a month of launch. They have to go somewhere in deep space and it takes a lot longer. It's actually kind of weird from our point of view because as we're kind of like the instrument developers, we kind of sign off on our hardware maybe like 2 years before it launches. So in some cases it can be quite a while before we kind of finish off a project in-house before we actually see it.
Wow.
Give data back.
I did not realize that it took that long of a process.
For sure, for the really big scientific missions, yeah.
Yeah.
It's often like multinational efforts. There's multiple parts of different instruments coming in from different places. That whole has to be integrated and kind of, you have instrument level testing and then they'll bolt that to the spacecraft and they'll test that again and there'll be, huge test campaigns because these are like $100 million spacecraft.
Right.
That you have to absolutely be sure works. So there's months and months of different levels of integration and testing before that even gets close to launch.
Yeah, definitely. I could understand that 100%. That's kind of something I had experience working in the electronics industry, working with Class 2 and Class 3 electronics, and especially with the Class 3, like, it's one of those things that has a lot of testing involved in, especially depending on what your customer is. And so it can take a long time just of rigorous testing to make sure that the product works exactly to the specifications of the customer and it has a high reliability and durability. That's pretty neat.
Yeah, for sure. Like we don't risk anything, so.
Right.
Yeah.
For sure.
That must be so, like a side note, that must be so cool to work on something and be like, that's in space, that's in orbit, or that's almost to the sun. Like, oh, that'd be so cool.
Absolutely.
So I actually haven't got anything kind of in space yet. As we're so far up the kind of the mission pipeline, it's not quite there on anything I've worked on, but yeah, I'm really looking forward to it.
Oh, that would be so cool. Wow. So slightly changing subject. I wanted to touch on this. So I remember a couple days ago I saw the whole thing with there potentially being regulations that would consider small satellites space debris. You want to touch on that a little bit? Explain what's going on and.
So a lot of this comes from all these new mega constellations that are being launched at the moment, and SpaceX Starlink is the biggest one that's been in the news recently. And lots of people are worried that these will result in catastrophic cascading space debris, and that's called the Kessler syndrome. I'm not completely convinced that those mega constellations themselves pose particularly high risk. Lots of those satellites are in very low orbit, so they decay very quickly. But because of that, because there's so many extra satellites that are in kind of low orbits now, there is a push to consider things like nanosatellites as not especially safe. This is kind of already a thing we have to watch for when we're launching things to kind of like the ISS orbit around 400 kilometers. And for lots of these nanosatellites are unpowered in terms of like propulsion anyway. So they are not able to take their own kind of evasive maneuvers. But because of all these extra satellites that are now being launched, there's a kind of a push to have a requirement to have these satellites with some propulsion if they're above a certain altitude.
Collision avoidance.
Yeah, so because there's so much other stuff out there, they need to have kind of the option to avoid things themselves, I guess. I don't know, especially if I agree with those numbers yet. I think some of the analysis has been done without assuming there's a difference in size between the satellites that would be involved. Mm-hmm. It's definitely something that needs to be looked at carefully.
Yeah.
There is not fantastic provision for tracking some of the smaller types of nanosatellites, especially like en masse, when there's hundreds of them being launched. So it's something that has to be improved in the future.
Mm-hmm.
I don't know if I agree that it's the right time to begin lots of regulation now in terms of like restricting where you can launch nanosatellites if they haven't got propulsion, for instance. But I don't think it's necessarily a terrible idea, but I think it's too early, and I think there are other systems that could be implemented that that isn't like a thing that needs to be mandated.
Right.
Basically.
What other systems were you thinking about?
So SpaceX have already demonstrated, I believe, and I think there's other people doing this as well, this autonomous maneuver avoidance thing, where they've got their own tracking, I guess, and they're constantly looking at different spacecraft and different collision chances. And if one of these gets within a certain amount, and I think it's normally like 1 in 10,000 is kind of like the acceptable risk, then they will automatically do some level of avoidance maneuver.
1 in 10,000. Wow.
I think that's kind of that sort of level is sort of like the acceptable risk benchmark kind of thing. So that kind of thing has been tested and I think is working at the moment with Starlink. But it's not infallible. Like, it can go wrong. And I guess sometimes the numbers get mentioned in like the press, and people go like, "Hang on a second, that's not cool." When someone mentions it's like 400 a month or something, I'm pulling numbers kind of out of nowhere at the minute, but like when people hear about the amount of autonomous avoidance things that are being done already, and then they extrapolate that to 12,000 satellites, and they go, "Hang on a second, this isn't sustainable."
Right.
But I don't necessarily agree that it has to be unsustainable. If it works, then it doesn't matter if you're doing 2,000. I mean, yeah, if you're doing 2,000 maneuvers a month, like that's a lot, right? But also, if it works, then kind of like there's no problem.
Right.
So I think it's too early to start making like sweeping regulation to fix the problem before we've had the tech developed to a point where it's the infrastructure is there to sustain stuff on this level anyway.
Right. So what do you think? When do you think would be a good time to start regulating? Well, I mean, I guess I think we can all agree space debris does definitely need to be regulated, but like specifically for having these strict regulations for small sats. Like, when do you think would be an appropriate time?
I think it depends when kind of this tracking technology matures, if it ever does. I know like different governments are looking at different better tracking stations, because lots of this tracking hardware comes back decades, right? Like it's a lot of it isn't particularly new, and lots of these nanosatellite type things haven't been around for very long. You know, like a decade, 15 years maybe. So I think we need to see that all these modern day systems can mature and make the avoidance problem better. I think the argument against these massive constellations comes from the fact that you can't really guarantee super high reliability on a 12,000 satellite constellation. Because if you're paying for really high reliability spacecraft, then you can't afford 12,000 of them. And it becomes a case of if you have 1% of those spacecraft that aren't operational and they're in certain altitude orbit.
Wait,
how many of that? Sure.
No, can you track? I thought that like all the nanosats have to have some sort of tracking, right? If they're sending and receiving data. Or is that
all the tracking is done. All the tracking is done from the ground. So it's done. I think it's mostly like the U.S. Air Force that do it. Where they will track with like radar systems and stuff and produce what's called two-line elements, which are basically a publicly accessible database of everything that's on orbit that they can see. And that's kind of like the baseline, which updates a few times a day, maybe. That's the baseline of like where your orbit is. And some spacecraft will have better ways of kind of working that out for themselves. But from like a ground-based perspective, there's like a objective to where we think the spacecraft is. For the smaller stuff, and when there's lots of stuff, that can kind of struggle a bit.
Right, right. So it's less of a trouble of like tracking from the ground and more having systems on the satellite itself that know where all the other small sats and space.
A little bit. I mean, part of the problem is can the ground-based stuff track the really, really small stuff? And I think the answer is tentatively yes, but not necessarily fantastically well yet. The other problem is if there's 12,000 satellites in orbit and 1% of those aren't working, at what point is it unsafe to have loads of things that don't have evasive capability?
Right.
When you've got 120 dead satellites, so it's kind of balancing. At what point is it fundamentally unsafe to have things above a certain orbit without any propulsion?
Right.
And I don't know that I've seen any really good numbers that kind of define that yet. But it's definitely a discussion that's going to have to be had at some point.
Yeah.
Right.
No. Yeah, that's...
Now, these satellites that are above a certain point, from my understanding, that CubeSats are basically meant to basically only have an operational life of, like, 25 years or something like that, and then, like, or 12 months or however long, and then, like, after a certain amount of time, then they are designed to fall, or on a course to fall back into the Earth's gravity well? And
sure,
burn up
so
an atmosphere, basically?
The recommendation is that you don't go over a 25-year on orbit after the end of the mission.
Mm-hmm.
And that's quite optimistic. A lot of things. It probably should be a lot shorter. The benefit of like CubeSats in like really low orbits, like sort of 400 kilometers, is that they come down a lot quicker than that.
Mm-hmm.
So they'll be down in like 12 months or so. So that's less of a problem. The issue comes more when it crosses orbits of important things, and the CubeSats kind of can't move out of the way because either it's end of mission or just because they're not designed to be able to. So the onus goes to the spacecraft that can move, and at a certain point, maybe that gets too much to be reasonable.
Gotcha. All right, that makes sense.
No. So, like, what are some, like, say for example, I'm sure you probably thought of this. Say for example, there is I don't know what effect you call it, but the cascading space debris, right? Like in the movie Gravity. What are some solutions that you've heard of, or do you like?
I think most of the solutions at the moment are preventative, not cures. So there are people like Astroscale who are looking to be able to deorbit finished satellites. Personally, I'm of the opinion that the issue isn't with the satellites in low Earth orbit. It's with the satellites above maybe 600 kilometers. So looking at high low Earth orbit or medium to geostationary.
Uh-huh.
And so the stuff in geostationary is purposely ended in a graveyard orbit. They boost up to an orbit that doesn't really have anything in, other than dead satellites. So that's not great because that's just filling up with kind of stuff that we finished with that aren't working anymore. But there are instances in geostationary orbit where there are dead spacecraft that have just failed and can't move. But with the stuff in really low Earth orbit, that tends to come down by itself over up to 25 years, maybe more, maybe less. It's the stuff from kind of an upper low Earth orbit to geostationary that I think is the bigger issue because it doesn't come down by itself.
Mm-hmm.
And there's plenty of things that in the past we didn't have these regulations where you kind of had to say this must come down in 25 years after end of mission or must go to a graveyard orbit. And there are plenty of things that are dead up there that aren't going to fix themselves. And that's the kind of thing that we have to have a level of solution for to clean up.
For the record, Graveyard Orbit sounds like a fantastic name. I don't know what for. Maybe a game, maybe a band, an album. I don't care. Graveyard Orbit. Love that name. Anyways, sorry. That was a tangent. So, are geostationary... So, what's the status with geostationary satellites right now? Like, do they still boost to a graveyard orbit, or, like...
So, but the 25-year thing is... It's like a regulation to dispose of your satellite, and that doesn't necessarily have to be you burn it up in the atmosphere. It could be you go to a graveyard orbit.
Okay.
But the two problems are, eventually that graveyard orbit is going to get very, very full of things that will come from geostationary orbit.
Right.
And the second problem is that sometimes stuff goes wrong in geostationary orbit, and you just can't. Your mission just ends there, and you can't do anything about it. Like maybe a micrometeoroid takes out a fuel line or something. Like there's plenty of things that could happen that just strands your spacecraft in a place and ends your mission right there. So those kind of things are the it's not sustainable at the moment, right? Like you have to have some way of either extending a mission or being able to suitably dispose of it afterwards.
Right.
And at this point, I think the general consensus is that the only acceptable genuine disposal is on an Earth escape trajectory or back into the atmosphere. Because graveyard orbits kind of aren't sustainable, in my opinion.
Right.
So lots of these kind of space debris companies are looking at kind of tackling some of these satellites that are in orbits that don't come down by themselves and possibly deorbiting them.
So what are these companies? How are they solving it? Are they like collecting it like a garbage collector and then like boosting down to Earth? Would they be?
I think that's the gist. So Astroscale I believe they have some level of like docking adapter type thing. And I think their plan is that they rendezvous with the satellite and kind of dock to it and drag it out of orbit. I think it was Surrey Satellite Technology in the UK did another mission recently where they were testing different capture mechanisms. So there was like a harpoon, like a net, and things like this. And the idea being if you like forcibly attach something that's got lots of drag, this is mostly for things like the higher, low Earth orbit satellites, maybe like 1,000 kilometers. You can attach certain systems, and that will naturally bring the satellite down. So there are a few different ways of tackling it, depending on kind of where the target is, really.
Right.
Interesting. Okay.
Talking too about not just small sats, but also you said you're kind of talking about like powered space vehicles. Notice on the website you also work with high-powered rockets. Can you tell us a little bit about that?
Ooh.
So the Flame Trench has lots of people who are very involved in kind of high-powered amateur rocketry. I'm not really one of them. It's not something we have loads of time put in at the moment. Charlie Garcia, who's one of our members over in the US, is quite involved in it. He used to be the president of the MIT rocketry team. And he works at a launch company in the US now. So he does lots of rocketry stuff for various different amateur projects. It's not something that we've massively looked at recently.
So
we've got so much other stuff going on, right?
Right.
There's only so much things we can try and build at the same time.
True, very true. I wasn't kind of sure if that was something that you kind of tied in with launching a method of launching CubeSats or whatnot, or kind of like an option to look at going forward.
I don't think so. So this kind of thing is like amateur stuff, so it's up and down.
Gotcha.
Getting to the point where you could launch into orbit is really, really difficult thing, and hundreds of companies have tried and failed. There's kind of like a boom in sort of like small sat development, in like small sat launcher development.
Yeah.
But I think only Rocket Lab has actually done it so far. So yeah, that level of stuff isn't something we're even attempting.
Gotcha. Yeah, I've been kind of reading up on like alternate methods for like getting up into space, because a rocket it's just so expensive to be able to have all these stages, burning all this fuel to get up out of the Earth's atmosphere. And I've seen some companies kind of trying to take an approach that I sort of thought too of how you could fly a plane at a high altitude, and then from that plane, say, launch a rocket from it up to the rest of the way out to the orbit that you want. I saw a couple of companies kind of taking a stab at it. I'm not sure how far they are yet, though.
Few of these, yeah. I don't know how viable a lot of them are. It's definitely a thing that's been done successfully. But the problem is they have to be kind of like commercially viable against the people who aren't doing it.
Yeah. And small payloads.
I haven't. There aren't any in operation at the moment. Other than I think Pegasus, but that's like a US military kind of one. It's not really commercial, although they do fly commercial missions, but it's operated like differently. So I guess if people like Stratolaunch or Virgin Orbit can demonstrate that they can do it sustainably, then sure. But they have to compete against the likes of SpaceX and Rocket Lab, who are flying up hundreds of small sats every couple of years.
Right.
And it remains to be proven if it's commercially viable. As like a technology, sure, yeah, it's been done. The thing. But yeah, in today's kind of space industry, when there's loads and loads of different companies trying to do different things, you have to be like commercially viable to exist.
Right. Yeah, and that's kind of one thing. I guess the traditional rocket does have an advantage over trying to launch from an aircraft carrier, or not an aircraft, an aircraft that's carrying small sats. Is the payload capacity, which rockets definitely have much higher capacity than the planes were that I was looking at. Yeah,
no, definitely. And so the Flame Trench, is that open source? Is that like an open source sort of movement, or is that more like, is it more closed source?
It's a bit of both. Depends kind of what project and what we're doing. The TFT Cube thing, the idea is to launch all of the stuff open source as kind of like when we have some designs. So there's different spectrums of open source hardware that I've seen. Some are like really community driven, and they publish everything from the start, and they really encourage community contribution throughout the development process. and others are kind of developed in source indoors until they have like a certain version that they know works, is tested, and they can publish and make open and say like, here we have this design for this thing. You guys go and do whatever you want. And that second one is kind of where we're operating. So when we have a platform that we think works and is a reasonable design to publish and say this is a reference design for a spacecraft we're confident in, then we will publish everything and make it all available. And people can build off that and build payloads for it or build their own from it, etc.
Oh, that's awesome.
But we're not like an open source driven organization.
Okay.
That makes sense?
Yeah, that makes sense.
We're just a group of people doing cool things, and if we finish a cool thing, then we might make it open source, depending on what the thing is. That's kind of the best way of describing it. It's a bit arbitrary. It varies between projects. Different projects are doing different things, so some make sense to open source things, others. So
yeah.
Right.
I'm honestly so excited for open source reaching space. Like, I think that I know I've talked about it before in the show, but because it just opens up so many more possibilities, and
I mean, it's happened already, right? Like the Libra Space Foundation has flown at least one CubeSat, and they're about to launch some Pocket Cubes. Foster Systems, who my co-founder founded, has launched one Pocket Cube so far, and there's another 2 going up in a few months, I believe. I've done it the exact time frame. But open source in space is definitely like pretty alive and well. Things like the Libra Space Foundation SatNOG system, which is kind of like an open source like ground station network for CubeSats and anything. Space station for commercial satellites. That's really popular. It's kind of not going anywhere, and it's only growing at the moment.
That is so encouraging to hear.
It really is.
Say I know, I'm sure we have some interested listeners. What is a good way to get started and get involved in contributing to what are the learning resources for people to start?
Oh god, there's so many, right? So I have a background in electronic engineering, so it makes it significantly easier. Most CubeSats are like 70% electronics by kind of like labor division, in my opinion. So having that kind of background is vital, personally.
Yeah.
If you don't want to start something yourself, the best way of doing it is probably just to in contact with people like Libra Space Foundation and see what they're doing and contribute to things like that. If you're more into trying to build something yourself, and for Pocket Cubes, that's potentially viable. They're not that expensive to launch. You're looking at maybe 25,000 euros up to launch Pocket Cube.
Oh.
If you've got kind of some electronics experience, that's pretty doable. You don't have to have like the really expensive rad hard electronics to do Pocket Cubes. Almost all of them are like off-the-shelf commercial components.
Like an Arduino or something. Yeah,
that kind of level of thing. In actual fact, that some of the chips in Arduinos are actually perform pretty well on orbit. I think it's the ATmega 128 that has some pretty solid on orbit data, even the non-rad tolerant version.
You know what? Actually, I'm going to switch. I was wondering this previously, and you're the guy to ask this to. So, how do electronics function differently in space?
Okay, so functionally, nothing changes. They work just the same as they do on Earth. 2 things to watch out for is temperature and radiation. So, obviously, electronics have an operating temperature range. And for space, you want to keep that as wide as possible, or you want to have really high confidence in your thermal models of the spacecraft. Because there's no atmosphere in space, so there's no convection and heat loss in that mode. So you have to be very careful about heat buildup. And obviously there's the sun, so the faces of the spacecraft that are in the sun are very hot, and the faces of the spacecraft that aren't are very cold. So thermal control in spacecraft is actually a really big aspect of spacecraft design. So being able to either control that or know what it is and like have an idea of what's happening with your spacecraft thermal model is really useful. But using things like industrial level components, I think it's automobile level, whatever they call it, is it like a good start? and lots of those have like really wide temperature operating measurements. So that's fine. The other one is radiation, of which there's kind of two aspects. So the first one is total ionizing dose, which is kind of what's the dose that we've picked up over all of our time in space. And that one for CubeSats doesn't matter so much because most of them are launched into a low orbit, and so they don't last very long in orbit like naturally. So that their lifetime limited, we call it, by orbital life, not by radiation. The second part of that radiation thing is basically what's called single event effects, and that's when you get hit by like a really energetic particle, and that causes bad things to happen in your electronics. So that might flip a bit, for instance, in memory or in some calculation you're doing. That's the easily correctable one, but you do have to make sure you check for it. Really bad one is called a single event latch-up, and that's basically when you have a high energetic particle hit the kind of the semiconductor in a chip, and it creates like a tunnel in the two different charge layers, and effectively it's like a short in the semiconductor, and that's really bad. And basically the only way to get rid of it is to try to detect it and then completely power cycle the component. And if you don't detect it, then it'll burn out your chip. So that's kind of when you see like rad hard components, hardness against both total dose, but also against kind of like how high energetic particles will negatively affect the component. So you have to, lots of the single event things can be kind of detected by design. You do have to be like aware of it and the kind of the modes that it affects it and how you deal with that.
Wow.
That's a lot more to think about than just, we're just going to throw a satellite in space.
Yeah, it's a really like multifaceted problem. There's a lot of stuff going on that you have to balance.
Yeah.
Now, is one of the solutions just adding more some sort of like radiation shielding on your electronics to kind of help pad them from ionizing events? And
so you can do a little bit where you have like small aluminium shields over the top of components, that kind of thing. That's a thing that people do. On CubeSats, you can't do much more than that because you're very limited in volume and mass. So you have to kind of balance it out in other. You can't just put it in a big box, basically.
Right.
What's called vaulting electronics is really good for stuff, but it's kind of terrible for really small stuff because it just doesn't scale down that well. Because you need like a thick piece of aluminium, right? Like it doesn't work at small scale.
Exactly.
Well, why don't you just use deflector shields?
If you invent some, we'll plan.
I can only imagine the amount of heat output on those. And energy requirements.
Right?
So tell us a little bit about the heat buildup, because this is something that's always kind of interested me a little bit. Like, I know, just from reading, it sounds like if you took a steak at room temperature and you just chucked it into space, it would actually take like almost a day out of sun to where it would actually like freeze, just because heat dissipation is so slow.
I can't say I've tried it. So basically, there's three modes of heat transfer, right? There's convection, radiation, and conduction. And on Earth, the main one is it's convection because the atmosphere wicks away heat really quickly.
Right.
But that doesn't exist in space.
Exactly.
So it's much harder to. It's called rejecting heat. And you have to be much more mindful of kind of how much heat you're dumping into your hardware. And also like the materials you've made your spacecraft of. So different materials will reject hardware at different speeds and will reject heat at different speeds.
Right.
That's based on effectively its emissivity. But there's all kinds of this extra level of material science and mechanical engineering that you have to consider. Less so when you're doing really basic small stuff, but once you start having like camera that's running for any significant period of time or some level of higher powered radio or that kind of thing, you have to start considering quite carefully kind of where all that power's going.
Right. because you gotta be able to get rid of the heat that it's been producing.
Yeah, right, exactly.
So I imagine on larger satellites and larger equipment or like on the ISS, I know that they have the heat sinks on the outside that help radiate heat out from the ship.
Yeah.
Or the craft. Is that something that also is utilized in the small sats, or are they just you just have to kind of
So it's used.
use
Those
the
kind of radiators are used a little bit in small sats, and here I'm using small sats as its actual definition, which is like 50 kilograms and up. A lot of the more common ways of doing it kind of at that scale are just really good insulation. So you want to keep the cold out or the warm in, or vice versa, and you mechanically design it so you don't have loads of really hot spots. That's kind of the only way to do it at the smaller scales, because the radiators are kind of big and complex and
right.
add significant amounts. They add lots of mass to the spacecraft compared to like the actual mass of what you're flying already.
Because it doesn't sail down well.
Yeah, and as far as I'm aware, it hasn't actually been done on CubeSats. Although that is something we're looking at Citadel, as part of like a hybrid system. I can't talk about that just yet.
Gotcha.
Wow. Well, thank you so much for hopping on and sharing a little bit about what you do. Love it. I'm gonna miss Space Month.
I know, it's been so much fun.
I know. Gosh, there's so much left to. I'm sure we'll visit it more some other time, because there's just
you could get another 10. You could get another 10 episodes out of that. There's so much stuff going on. It's ridiculous.
Easy. Oh, it's so exciting. Anyways, is there any social media, anything you want to plug?
Yeah, so my Twitter is @_Ben_in_space. And then the Flame Trench is @theflametrench, and Citadel Space Systems is @Citadel Space Sys, all one word. And you can find us on all of our different websites, and most of them are linked between each other.
Okay.
Please go and have a look and see what we're doing.
Yeah, I'll throw a couple of them in the show notes. Yeah, that's great. And as always, if you're on Apple Podcasts, rate us, review us, like us, follow us, all that jazz. And next month we'll be doing entrepreneur. I cannot.
Entrepreneurs.
I need to thank you. I need to just listen to that word, practice saying it right. But yeah, we're going to explore going from project to business and kind of what that looks like. And there's a lot of you out there who are in this process, and I'd like to walk you through kind of all of it and talking to different guests. So that'll be a lot of fun. Definitely want to stay tuned for that. And let's see. I know I'm forgetting something. Oh yes. Also, we just finished the game jam, and it was a blast. So much fun. So go to Jamcraft. You can look at the submissions. You can rate us, or rate other games too. Play them. Anyways, have fun working your projects, everyone. And remember, whatever you're working on, keep it janky to the max.
Hey everyone, thank you for tuning in to this episode of Jaynky to the Max. If you like it, make sure to like the video and subscribe. And if you want to suggest more projects that we can feature, make sure to comment down below, or even better, join the Discord server in the description. We try to stream live every weekend on the server, so make sure to join and grab the podcast role if you want to be there and see it for yourself. Anyway, make sure to stay janky.